Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video we're going to go over some properties of logarithms. We're going to learn how to expand and condense statements with logarithms in them, and we're going to learn to approximate results under certain situations. So let's begin with the properties of logarithms, and all the properties on this page: x is positive, y is positive, a is positive but not equal to 1, and r can be any real number. The first one, log base a of 1, that is equal to 0. And again, that's because a to the 0 power equals 1 for some positive number a. Log base a of a, that is equal to 1. So when the base and the argument are the same, the logarithm is equal to 1. And again, this is because a to the first power equals a. Now on to a few properties that are really useful. The first is the product property, and it says that if we have the logarithm of a product, x times y, and let me just bind those together like that, then that is equal to the sum of the logarithms of those factors, log base a of x plus log base a of y. So let's go over why this is true. And as we get into college algebra, this is where we start to prove that some of these things are true rather than just accepting that they're true. So let's do that. Here, the best way to prove this is to start by saying, okay, let's assume that those two logarithms are equal to m and n, two numbers. So log base a of x is equal to m. That means that a to the m power equals x. That is converting that to exponential form. Also, for the same reasoning, log base a of y equals n becomes a to the n power equals y. Picking it up from there, we know that x times y equals a to the m times a to the n power, and one of our rules for exponents tells us that we can add those exponents, so it's a to the m plus n power. Now we can rewrite this in logarithmic form. Log of the base a of x times y equals m plus n, which is what we were claiming. It's log base a of x plus log base a of y. So there's a lot of rules for exponents that apply to logarithms as well, and this is one case where that happens. We can do the same sort of approach for the next property, the quotient property. This says that if we're taking the logarithm of a quotient, we can convert that to a difference, subtraction, of two separate logarithms, the logarithm of the numerator minus the logarithm of the denominator. And if we use the same setup, again, assuming that log base a of x is m and log base a of y is n, then x over y equals a to the m over a to the n power, which we know we can simplify that by subtracting those exponents, a to the m minus n power. Now, if we change this to logarithmic form, log base a of x over y equals the exponent, m minus n. But that equals log base a of x minus log base a of y. Finally, the power property says that log base a of x raised to some power r can be rewritten as r times log base a of x. And we'll prove this one using the product property that we had up above. And maybe I'll leave it right there. So if I've got log base a of x to the r power, I can rewrite that as log base a of x times dot 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 times x, where there are r of these. Then I can break that by the the product property into the sum of our different logarithms. Log base a of x plus log base a of x plus dot 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 plus log base a of x, where that happens r times. And so I can rewrite that as r times that logarithm, proving that property. Okay. To finish, there's a couple here that we'll use in a later section, but I wanted to introduce them here. First, if we raise a to the log base a of x power, and I know it seems weird that we would want to do that, but that's simply equal to x. Remember that log base a of x is what power do you raise a to in order to get x? Well, we're raising a to that power, so we must get x out. For the other one, log base a of a to the x power, that also just equals x. And basically what we're asking on the left side here is a to what power equals a to the x power? Well, clearly that's got to be x. So we'll use those. Think about the inverse ideas that we had before. This is really what's happening here. Exponential of logarithm with the same base, they undo each other, and it doesn't matter what order those are in. All right. There are three types of homework problems that typically come from this. One is where we try to expand a single logarithm into multiple logarithms, each of a single factor argument. So the first one, we've got log base a of x cubed, y squared, square root of z. The product property allows us to rewrite this as log base a of x cubed plus log base a of y squared plus log base a of the square root of z. Then the power property allows us to take the exponent for each variable and rewrite it as a factor in front of the logarithm. So take the 3 out to the front, and that's 3 log base a of x, plus bring the 2 out, 2 log base a of y, plus, is there something we can bring out of that last one? Well, remember that the square root of z is equivalent to z to the 1/2 power, so I can bring out a 1/2 in front of log base a of z. Now this is expanded. We have 3 simple logarithms, logarithms of a single variable or factor. That's called expanding. Notice what happened. We can do these in the same step. The exponents became factors, and because we were multiplying them all, they all became add-ins. We were finding the sum. In general, use the same approach in problem B, except the factors from the denominator are going to be subtracted by that difference property. And so in one step, I can rewrite this. Okay, what's the exponent for x? It's 1. So I'm just going to write log base a of x. Y is in the numerator, so that's adding. The exponent 3 becomes a factor, so that's 3 log base a of x. Now in the denominator, these factors are going to produce logarithms that are subtracted. Minus 4 log base a of z. Didn't really give myself enough room here. Minus 5 log base a of w. One more to go here for expanding. And remember that the mth root, the root whose index is m, is really equivalent to an exponent of 1 over m. So I can rewrite this first as log base a of r to the 3 over m all over s to the 4 over m t to the 7 over m. Now those exponents, remember, come out as factors. The ones from the numerator are going to be positive. The ones from the denominator are going to be negative. So we get we get 3 over m log base a of r minus 4 over m log base a of s minus 7 over m log base a of t. One last thing about the denominators. Let's say we have a simple one like log base a of x squared over y cubed. And we know that we ended up subtracting the logarithm with y in that case. Think of it this way. Y to the third in the denominator is the same as y to the negative third in the numerator. So we could rewrite this as log base a of x squared y to the negative 3. And now you can see when that negative 3 comes out as a factor, that's why we're subtracting the logarithms that came from a factor in the denominator. Right. Condense is the opposite. Rather than breaking it up into separate logarithms, sometimes we want to get all the logarithms together into one. And so that's what we're doing here. I've got a few examples of that. The thing to remember, right, just undoing what we did in the last type of problem, is anything that's positive goes in the numerator, anything that's negative goes in the denominator. Any coefficient in front becomes an exponent for that variable. There are no coefficients in part A, so this can just become log base A. X is going to be in the numerator because it's positive. Y is in the denominator because it's negative. Z is in the numerator because it's positive. That's the way we can condense those three separate logarithms into one. For B, same idea. Log base A. I take a quick glance and I see some positive, some negative, so I know I'm going to have a fraction. And now I just start placing them in the right spot. So x was in a positive logarithm. Its exponent is going to be 3, and it's going to be in the numerator because it was positive. The same for y. We're going to have y to the fourth in the numerator. For z, because it's a negative factor of 5, that's going in the denominator. That's z to the fifth. And then finally, w to the 1/2 power, we can rewrite that as the square root of w. We're not going to worry about rationalizing that denominator, just applying the square root. 1/2 power is the same as a square root. C is a little tricky. What do we do with that 2 that's out in front? Right? I want that in terms of log base A. So I've got to figure out what logarithm base A would give me a result of 2. And this is really the same as log base A of A squared. And so I could also move that 2 out to the front of that if I wanted to write it that way. But I'm going to have log base A, and I have some that are positive, some that are negative. A is positive, that's A squared. The x is negative. It doesn't have a factor other than 1 in front of it, so that's just an x in the denominator. And then on top in the numerator, y to the 9th power, because that was a positive logarithm. All right, one last type of problem to go through, and these end up in a lot of textbook problems, maybe test problems. You're told what one logarithm is approximately equal to. We'll learn how to find that in a later section. And we want to rewrite other logarithms in terms of that logarithm so we can calculate what it's equal to. So in this example, I know log base 10 of 7 is about 0.845. And I need to find log base 10 of 343. The trick with this one is to realize that 343 is 7 to the 3rd power. By the power rule, I can move that 3 out to the front as a factor. 3 times log base 10 of 7. And from above, I know that log base 10 of 7 is about 0.845. So this is approximately 3 times 0.845. Multiply that out, and we get 2.535. I think that's right. Yeah, that is right. For the second one, log base 10 of 100 sevenths. So I can use the quotient rule here to break this up into log base 10 of 100 minus log base 10 of 7. And the good news is I already know what log base 10 of 7 is. From above, that's 0.845. What about log base 10 of 100? Well, think about in terms of exponents first. What power do we raise 10 to get 100? 2. We could also rewrite 100 as 10 squared and bring the 2 out to the front, and we've got log base 10 of 10, which is 1. But anyway, this is 2 minus 0.845, and that is 1.155. All right, that is the last video for this section. I'll see you in the next section.